All right, week 9, chapter 7. So in this chapter we have intermolecular forces, which we've seen several chapters in a row. It's all based on electronegativity and how one molecule can interact with another. So in this chapter we're going to look at phases of matter first. We talked about those in week 1, chapter 1, but now we're going to have a new kind of look at how each atom and each molecule can interact with one another. Specifically from molecule to molecule. And then we'll talk about the predictive forces based on polarity, like London forces, dipole forces, and hydrogen bonding being the one that we talked about most in the biochemistry chapter. Lastly, we'll remind ourselves that molecules gain some strength, but they're nowhere close to non-molecular substances that have metals. So we'll see a direct comparison to those at the very end of this chapter. So as we introduce intermolecular forces, we have to understand the word intermolecular. You can imagine that intermolecular is a lot like an interstate. Interstates go from state to state to state to state. So when we look at this chapter, we're looking at how does one molecule attract another molecule to another molecule to another molecule. We've seen in previous exams and previous homeworks intramolecular forces. Those are ionic and covalent bonds. What we're going to focus on mostly this time is what happens to a molecule and another molecule separated by space. How do they attract each other through their electronegativities? This is a lot like molecular glue. So it's kind of like what kind of glue is holding those molecules together. We'll see a superglue called hydrogen bonding. We'll see a Elmer's kind of glue we call dipole forces. And then we see the kind of sticky note glue that kind of peels off and on for dispersion, also called London forces. So as we look at this picture here, we see this really heavy truck traveling across the ice. What we need to realize is the only thing that's keeping that truck from sinking to the bottom of the lake is some water molecules. So beneath the truck is some little H2Os. And their ability to attract other H2Os, this is the glue. And that glue is strong enough to hold the truck up. Because what we have to remember is it's not just a few water molecules below that truck. If we want to know how many water molecules are under that truck, let's think of just one drink of water. One drink of water would be 602 trillion water molecules. So let's draw all those zeros out. So there's 3, 6, 9, 12, 15. So we need 18 and then 21. So commas. This is how many water molecules are in just one drink of water. If you look at that number, we'll see it again later as we get towards exam 5. But if you win the lottery, you win maybe $1 million. That's in this position here. If you want to think of billions of dollars, you would be in this category here. If you want to look even further to how broke the United States is, we're looking at, say 30 trillion up in here. But this is another 602 trillion of those trillion. And that's how much is in this one little drink of water right beneath that tire. But if this is 2 feet of ice or even a foot of ice, there's trillions upon trillions upon trillions upon trillions of water molecules, and they all have this glue holding them together. So our job in this chapter is to identify that glue, specifically this kind of glue here, and for very polar bonds, that's called hydrogen bonding. So all of this glue that holds these water molecules together is strong enough to hold that very heavy truck up on that ice. So as we start to look at phases of matter, now we should have a new perspective on what it really means. So in a solid phase, what happens is you're glued on all sides. If you're glued on all sides, that means you can't move. So you have somebody on the right, on the left, on the top, on the bottom. But you also have one in front and then back because molecules form together in 3 dimensions, not 2 as shown on this picture. So if you're glued on all sides, we call you frozen. And the biggest misnomer of a solid is you have to be frozen, and in order for it to be frozen, you have to be cold, and that's not the case. It just depends on the material. Sure, ice might be cold when it's frozen, but other things like gold, when they're frozen, they're not cold at all. They're just in the solid already at room temperature. Imagine if you start breaking some of this glue. So if you warm this structure up and you break a little bit of this glue so that it's only connected on a few sides, notice now these molecules can start moving around. And as they start moving around, they have a fluid kind of motion, and this is what we call the liquid. So this is what happens when you have a little bit of glue, but you're not glued on all sides. And the only way to do that is to kind of warm up those molecules and weaken some of that glue. Eventually, if we break all attractive forces, so there's no glue holding anybody together, now we can move wherever we want. And because there is no attractions, they just kind of bounce around, fly around, and this is exactly what it means to be in the gas phase. So in the gas phase, we have no real shape. We're going to fill the container no matter what, whereas a liquid would only fill the bottom of the container. A solid would have a fixed shape and it wouldn't fit the bottom of the container at all. It would be very rigid. So the major differences between a solid is glued on all sides, fixed shape, fixed volume, very durable, very rigid. A liquid's going to have less glue, so still somewhat of a fixed volume because it still sticks together enough to make a puddle, but it doesn't have squared kind of rigid edges like a solid would have. And then if we remove all the glue completely, this is when we become a gas. We're going to have an infinite shape because we can expand and diffuse across the room, and that's going to again expand our volume at the same time. So when we look at temperature, temperature is one of the greatest ways, or at least the fastest ways, to recognize strength. The higher the temperature, the stronger the glue. So if it takes 0 degrees to break your glue, you're pretty weak. If it takes 1,000 degrees to break your glue and start melting you, that's pretty strong. So just relative temperature can give us a great idea of when the glue is starting to break, when it's completely broken. So as we look at, say, condensation and evaporation, evaporation would be the point at which all glue is broken. Condensation would be the point at which glue starts to form. If we look at melting and freezing would be when some of the glue starts to break, that would be melting. And then when we start forming it completely together, gluing it on all sides, that's when we would be freezing. Those temperatures happen at the same time. It's just a matter of, do we continue heating past that point, melting, or do we continue cooling past that point? That would be freezing. So in these kind of cyclic processes, just remember that they happen at the same temperature. It's just a matter of, if you're going to vaporize something, you're going to continue to heat it past this temperature. And if you're going to condense something, you're going to cool it past that specific temperature. So it is a two-way street. You can go either way, and you can be in kind of an equilibrium between these two phases at that temperature. But it depends on, if you add more heat, you're going to get more vaporization. If if you remove that heat, you're going to get more condensation. The same would go for melting and freezing. If you keep removing the heat, you're going to freeze it completely by allowing it to glue on all sides. If you warm it up, you're going to increase the melting by breaking more of those glued kind of interactions. So boiling point is a great way to recognize when does all the glue break. And if we have a comparison between things of high temperatures and low temperatures, just remember that high temperatures are strong, low temperatures are weak in their glue and their intermolecular forces. So we take a closer look at freezing point. Here's a picture that kind of shows you what's going on. We have a very organized structure of molecules, in this case water. And notice that they have this perfect shape. But as we weaken some of this glue, notice we start to jumble apart. Because we start to weaken our glue, we start to tumble, we start to squish together. This is exactly why when water freezes in this direction, they expand to allow for that perfect distance for that hydrogen bonding to form. And that's also why when you melt, in this case for water, you're going to be now more compact, or in essence shrink. Turns out water and ammonia, so H2O and NH3, these are the only two molecules that expand when they freeze. Most things, when they get cold, they shrink. No different than a basketball doesn't like to bounce when it's cold. The fact that water and ammonia actually expand is because they have to acquire this specific distance in order to accommodate hydrogen bonding. And because they can hydrogen bond on all sides, and very few other molecules can on all sides, these are the ones that actually get bigger when they freeze, which is bad for pipes, say in the wintertime when they freeze. So as we look at the three phases, we just need to make sure that we understand that solids are glued on all sides. And if you want to break that glue, it's going to require an increase in temperature. To get them moving, to give them kinetic energy, we're going to have to add heat. And if we add enough heat, the glue can start to break and our solid can become a liquid through that melting process. But it can also be removed and refreeze in that same kind of instance. So our job in this next video will be to recognize intermolecular forces so that we know which type of forces are attracting each other in those molecules. And then just remember kind of in the back of our mind that if things were glued on all sides, we'd be a solid. If things were glued on a few sides, that would be a liquid. And if we reach the boiling point, we can break all glue and become that gas phase, which we'll see again in week 16.